I'm Taylor Jones from UNT. Thank you for the invitation, and thank you for coming and listening. So I'm going to be talking about fractal geometry. Nothing too in depth, since this this subject kind of requires many different branches of math. So like dynamics or probability or measure theory. It makes use of lots of different stuff. So I'm just going to give some very introductory background and one application of what a paper that I have submitted for publication recently. So let's get started. Okay, so what's a fractal? I don't know. And there's not actually a definition for one. So, but you'll recognize it. You'll recognize one whenever you see it. So here's a few cool ones that I like. So I have this highway dragon curve here, and this one's pretty famous, the Mandelbrot set. So what do you do when you, what kind of questions do you ask when you see a fractal? The first question is, what's its dimension? So to answer this question, we have to come up with a definition. So there's several definitions for dimension. I'll give you the two most common ones that are studied. So let's start with the box dimension, but I want to start with some motivation. So if you look at the volume of spheres and cubes in Rn, then they have this kind of relationship. So like the volume of a sphere is some constant which depends only on n times its radius to the n. So these like n-dimensional objects have this kind of relationship with their size or their measure. So we want to capture this ideal. We want to generalize it for all kinds of sets in a way that allows us to have non-integer dimensions. So how do we do that? So we want something like this. So maybe I'm being a little vague here. What do I mean by size? But we want some kind of relationship like this that's similar to this. Okay. So whenever we look at the measure of a set, how do we approximate this? We'll usually cover that set by things that are easy to measure, and then add up those things, and we get this nice approximation. So if I let n delta be the minimum number of boxes, so just n-dimensional cubes, I need to cover my set F. Then I would want this to be a good approximation of my size of F, provided S is the dimension that I want F to be. So when delta gets small, so when I cover my set with smaller and smaller boxes, I'm going to be needing more and more of them to cover my set. So this n delta is going to go to infinity, and this delta S is going to go to 0. So if S is too small, right, then this n delta is going to overpower and take this limit to infinity. If if S is too big, then the delta is going to overpower, and this will go to 0. So if S is quote unquote just right, then you'll have this sort of asymptotic relationship when delta goes to 0. And so solving for S, you would like to see this. So this leads us to our very easy and intuitive box counting dimension. So if this limit exists, then we'll say this is the box counting dimension of F. You can also, so again, this limit may not exist, and it's not too hard to come up with some pathological examples. But you can also say, okay, the lim sup and lim inf will always exist. So you can say those are the lower box counting dimensions and upper box counting dimensions. And if they agree, we'll say, okay, here's our box counting dimension. So this definition has some problems with it. And a way to resolve those is to give kind of a harder definition, but this will work for all sets. So the Hausdorff dimension. So we'll define this thing H delta S. So this is the inf of all of these sums where these UIs are a cover of our set F, delta cover. So what a delta cover means is this thing covers F and its diameters are all at most delta. So with the box counting dimension, you cover your set by these boxes that have exactly size delta. For the Hausdorff dimension, this is much more relaxed. We're covering these things whose diameters is at most delta. And then just like before, we want to take delta to 0, except here, now we're guaranteed this limit to exist since this thing here is increasing in delta. Since, of course, if I take delta 1 smaller than delta 2, then every delta 1 cover belongs to the set of delta 2 covers. So since we're taking the inf, these things are getting bigger when delta gets smaller. Okay, so now we arrive at our definition. Well, okay, you kind of need a lemma, but I'm not going to prove it. So if S is too small, again, what's going to happen is this S-dimensional Hausdorff measure. So this is going to be infinite. And if S is too big, then this will be 0. And if at some point, but there's like the smallest point where it's finite, and that will be the Hausdorff dimension. So this is it's kind of better to take your time to absorb it, but it's kind of a fast talk. So I do want to do one application. So this is a paper that my colleagues and I have submitted recently. So here's a fractal in the real line. This is kind of a cool observation. If you look at this continued fraction, and then if you look at its decimal expansion, so this is base 10, you'll notice that we have these things line up pretty neatly. So these things are called Trot numbers. So here's our definition. Is this okay? That's not a good definition. Okay, it's a Trot number in base B if it's base B expansion and its continued fraction match in this sort of sense. Okay, so the first natural question is, do these things exist? And if so, what's the dimension of this set? So we have proved existence, and we have classified all the bases for which they exist. In particular, you may notice, so base 10 is a good base, which I think is kind of maybe philosophical. Like if we had failed this question right away, we might have never thought about it more. But because base 10 happened to work, like experimentally, we thought more and found all the other bases. So if their base is not good, then this is empty otherwise. And then the dimension is strictly less than 1. And in fact, the union over all good bases, the dimension of this is still less than 1, Hausdorff dimension. It is still open whether this has positive dimension. So the lower bound usually is extremely hard when making calculations of dimension. The upper bound is usually very easy because of this thing here. When you take the inf, you just need to witness like one cover, and then whatever calculation you get there, boom, that's an upper bound. But because you're taking the inf, the lower bound, you have to know like it's got to work for all covers really. So this is why lower bounds are really hard. This set, a lower bound for this set would be quite hard because you don't have an IFS that generates this particular fractal, and so it's a little bit hard. But I do suspect this does have positive dimension. It does look like there's kind of a Cantor set that lies inside here. But anyways, that's I think I have to say thank you. Right. Oh no, this is the last slide. Okay. I thought this morning I put a slide that said thank you, but it's gone. So this must be the old.
Stop recording. Let's thank the speaker. Thank you.